Hello, welcome to TTIC 31230, Fundamentals of Deep Learning. This is going to be a motivational segment unit. Administrative details can be found on the course webpage, which you presumably have found if you're seeing this video. This is going to be a discussion of the history of deep learning. And I'm going to try to consider the issue of whether there is now a Moore's law of AI, the idea that every year we're making significant progress. So as I go through the history, let's keep that question in mind. So we're going to start with some very old history. So in 1943, McCulloch and Pitts introduced what they called the linear threshold neuron. The linear threshold unit remains a kind of keystone of deep learning. So this was a really fundamental step. In 1962, Rosenblatt applies or develops a Hebbian learning rule, and Novikov proved the perceptron convergence theorem. If you've taken a course in machine learning, you've probably seen the perceptron convergence theorem. It's a really classical result. In 1969, Minsky and Papert published a book entitled Perceptrons. And this book had a lot of negative results, negative theorems. For example, they proved that a linear threshold unit could not, in principle, count the number of connected components of an image, of a foreground segmentation in an image. And these negative results sort of put a damper on neural network research from that point forward through the 70s. In the 60s and 70s, the intellectual foundation for AI was often taken to be mathematical logic. And if it wasn't mathematical logic, it was some other symbolic method. So symbolic methods dominated AI through the 1970s. And then in the 1980s, there was a bit of a renaissance. So in 1980, Fukushima developed something he called the neocognitron, which was a form of convolutional neural network applied to vision. In 1984, there was a big theoretical advance. Leslie Valiant at Harvard defined probably approximately correct PAC learnability. And the development of PAC learnability really stimulated the theory of machine learning. And Valiant won a Turing Award in 2010, much later, for this kind of revolution in machine learning. In 1985, Hinton and Sejnowski introduced the Boltzmann machine. We're not going to talk about that much, but it was very influential at the time. And in 1986, Rummel, Hart, Hinton, and Williams demonstrated empirical success with backpropagation. Backpropagation itself was much older, dating back to 1961. But the realization that this was an effective way of training neural networks and sort of an engineering demonstration of the power of backpropagation did have a lot of visibility and influence at this time. Then in the 90s and the aughts, neural network research was sort of in the shadows. There were important developments, but the papers were not big events. They were sort of not prominent papers. In 1997, Schmidt-Hubert et al. Introduced long short-term memories. This is kind of a shocking development because it was, largely an intellectually motivated, intuitively motivated, but it turned out to be very important later on. Up until just a couple years ago, LSTMs or variants of LSTMs were really a dominant paradigm in natural language and speech. They've been sort of supplanted now by the transformers. We're going to talk about that later in the course. Okay, so in 1998, LeCun introduced convolutional neural networks, LeNet. That got some visibility, but it wasn't the dominant approach to vision at that time. Bengio introduced neural language modeling in 2003. Again, these were important things ultimately, but were not very prominent at the time. Okay, the current era. This is when things get really exciting, really start to move. Most people, if asked, when did the deep revolution start, they point to this one event, AlexNet dominating in computer vision competition in 2012. So computer vision had kind of plateaued at that point. There were these graphical models, the deformable part model, although performance had been making a lot of progress from about 2007 up until about 2010, 2011, it had sort of plateaued. And Imagenet was new at that time. It was a very big data set of images, millions of images. And there was a new evaluation that was getting a lot of attention, and there was a particular workshop where AlexNet just destroyed the competition. All the other machines were at about the same level, all the other entrants, and AlexNet just had a far superior performance. At that same year, Google speech recognition converted to deep learning. So deep learning took over speech recognition. And both of these developments, AlexNet and the revolution in speech recognition, came out of Hinton's group at Toronto. And then the progress just continued. In 2013, various systems that were based on AlexNet, sort of variants of AlexNet, continued to dramatically improve computer vision. In 2014, neural machine translation appears, sequence-to-sequence models. I remember this talk at NeurIPS by Ilya Sutskever, and it was a fascinating talk because he was trying to make the point that we don't need to understand anything. We can just let the neural networks figure it out. And he made this sort of very controversial statement of minimal innovation for maximal effect. And his point was, you don't have to think very hard. You just design the right architecture and let the machine, let the deep learning handle it. You don't, a very naive approach to the design of the deep system can work. At about the same time, there were important architectural innovations, variational autoencoders, and we'll talk about that later in this segment and also later in the course. Variational autoencoders are a way of, primarily were introduced as a way of modeling vision, images. In the same year, generative adversarial networks appeared, GANs. You've probably heard of that. That's a sort of a fundamentally different way of modeling distributions involving adversarial training. In the same year, graph neural networks appeared, and these revolutionized the prediction of properties, chemical properties of small molecules. And dramatic improvements in computer vision and speech recognition continued through to 2014. Okay, 2015, Google converts to neural machine translation. So this was a major revolution in their internal research groups. A lot of, some research groups who weren't doing neural methods were not very happy when they were told they had to start doing neural methods. But it did lead to dramatic improvements, particularly in English, Japanese. That same year, ResNet appeared, the concept of residual connections. Residual connections have become another keystone of deep architectures, but it only appeared in 2015. And that immediately made another dramatic improvement in computer vision systems. 2016, AlphaGo defeats Lee Sedol. So AlphaGo came out of DeepMind. This was a huge media event. I'm sure you all were aware of this when it happened. In 2017, a later version of AlphaGo called AlphaZero, and AlphaZero was general. It could be applied to various games. So they applied it to Go, chess, and shogi. So AlphaZero learns to play a game given nothing but the rules of the game and self-play. So through self-play and the rules of the game, in a matter of hours with vast computational resources. So when you say a matter of hours, you're meaning it's maybe 100 years of human time in terms of the number of games played. So in a matter of hours on supercomputers, through self-play, it advances computer Go and computer chess far beyond human abilities. In a matter of hours, it was at a superhuman level, and then if you let it run for 40 hours or weeks, it's completely beyond human play. Another thing that happened in 2017 was unsupervised machine translation. Here you take a big pile of English, say, and a big pile of German, and with no alignment, no translation pairs, and you learn to align English sentences with German sentences. You learn to translate English to German. It's not as good as supervised translation, but it's shocking. I found it shocking that this can be at all. Okay, another thing that happened in 2017 was a really shocking progress in GANs. So in 2017, generative adversarial networks were able to generate high-resolution, realistic face images of people that did not exist, just sampled faces. In 2018, there was a lot of progress in what we normally would think of as natural language understanding. And I'll talk about that in more detail in a moment. So another thing that happened in 2018 is AlphaFold. AlphaFold also came out of DeepMind, and it revolutionized the prediction of protein structure. That's a really old classical problem in biology. So it's a really significant development to be able to do protein structure prediction much better than had been possible in the past. There was also more improvement in GANs. Style GANs led to another dramatic improvement in generation of face images. And in 2019, there was what I find to be a very fascinating development. Variational autoencoders is a very different architecture, very different way of training models of probability distributions from GANs. And they'd always been non-competitive with GANs at generating images. But in 2019, a new form of variational autoencoder, the vector quantized autoencoder, demonstrated that it could be competitive with GANs at generating images. Okay, this question of Moore's law, I just want to sort of summarize, end on this point. This question of Moore's law is interesting. Are we making significant progress every year? When I taught this course in the past, every time I taught the course, I could point to something that had happened in the past year, since the last time I taught the course, that was a dramatic, clear, objective, dramatic progress in artificial intelligence. This year, to me, it's less clear. It's been less time. It's only been 9 months since I taught the course before. The one thing that's happened that's gotten probably the most attention in that period is this new language model called GPT-3. And there was an undergraduate who took this language model and got a lot of attention by getting it to write a blog post. So the way this works is you give the language model an opening sentence, like to have a lot of impact, you have to be bold and creative. And then the language model continues from that sentence to fill out a blog post or an article. And this undergraduate understood what GPT-3 was good at. It's good at flowery sentences on topic, but it's not very good at logic and being logically consistent. So these sort of self-help articles with a lot of generic statements, like being bold and creative, sound like they're written by people. And this particular blog post achieved the #1 position on Hacker News. So, and this got a lot of press. But it's unclear to me, I don't find this to be a really objective, clear progress. It's clear whether this is more of a parlor trick. So we'll see if it's the case that deep networks may be saturating in the dramatic improvements. Back around 2010, computer vision had kind of saturated. And although I had been claiming that there was this Moore's law, there was a year or two, year and a half, when it seemed like the progress wasn't there, no dramatic progress. So it would be interesting if deep learning has now reached that phase where it's going to kind of plateau. It's an interesting question. All right, but I want to go over, again, go over in more detail some of the things that have happened. So one thing that's happened is progress in natural language understanding. So there's this benchmark that's been developed, the General Language Understanding Evaluation. And this is a suite of a bunch of problems. This is sort of the best people can do at designing objective data set tests for natural language understanding. And includes things like paraphrase, or is this sentence saying the same thing as that sentence? And that seems fairly semantic. There's also something called natural language implication, NLI. So does this sentence imply that sentence? And question answering problems. You know, you're given a Wikipedia article and you're asked a question and you have to find the answer in the article. There's a great co-reference task, the Winograd task. Anyway, these tasks are the best thing people can design, have come up with to measure the performance of computers at understanding natural language. So here's the leaderboard for GLUE. And what's happening here, this is the leaderboard as of a year ago. What's happening here is that these systems are superhuman on these tasks. So for each one of these tasks, you have people solve it and they get some score. And if you look at this leaderboard, the 9th entry is the human baseline. And all of these other entries are somewhat above the human baseline. So this is kind of strange. So this is saying that these computer models, and I should say these computer models are based on, they start with a language model. They start with just something trained on a huge corpus of English to build a model of the probability distribution over English sentences. And then they're fine-tuned for these understanding tasks. And this approach seems to have solved, you know, you could argue that they've solved these tasks at a superhuman level. But the problem here, most people agree now, is that these data set tasks are not really capable of measuring the machine's ability to understand. None of these machines can engage in dialogue in a way that's compelling. If someone engages in dialogue and they knows how to probe the understanding of the machines fail. So the problem is more with the benchmarks. Nonetheless, this is a dramatic development. This is a harder benchmark. Superhuman performance has not quite been achieved on this benchmark, but you can see that it's close, 89.3 versus 89.8. Okay, now I'm going to talk about GANs and variational autoencoders. And again, the issue here is there a Moore's law? So this is GANs when they were introduced in 2014. This is from a talk that was given at ICLEAR, International Conference on Learning Representations, sort of the main deep conference, by Ian Goodfellow. And Ian Goodfellow was the creator of GANs. And this is showing face generation through a 4-year period from 2014 to 2018. And this is showing dramatic improvements. In 2017, people felt that this particular model called progressive GANs had produced really shocking images. These people at these higher resolution images do not exist. We're sampling from a probability distribution over human faces. So it's generating images of people that do not exist. This last image from 2018 is from something called Style Gans. And Style Gans seem to be a kind of last word. It's hard to imagine generating more accurate face images than Style Gans is able to generate. It's able to generate variation in the position of the hair strands in a person's head. It's shocking. For Imagenet, GANs don't do as well. Faces seem to be particularly easy for GANs. You can generate images of faces. But when you go to Imagenet, Imagenet has images of everything: dogs, cats, butterflies, flowers, mountains, trees. So when you try to build a model of images in general, of sort of natural images generally, it's much harder. But you can do something called class conditional GANs. So you say, give me an image of a flower, give me an image of a dog. So when you tell it what you want it to generate, and it builds a different model for each class, the model of dogs is different from the model of flowers, it does better. And this is progress in class conditional GANs for ImageNets, for Imagenet. So you can see that dogs, for example, have gotten a lot better. And again, this dog does not exist. This butterfly has 4 wings and is missing a head, so it clearly doesn't exist. But nonetheless, it's kind of shocking. Variational autoencoders. As I said before, variational autoencoders were never competitive with GANs in terms of the ability to generate images, but they have certain advantages. With a GAN, you're never really sure if it's covering the space of all faces. If there's some kind of face that's missing, that's very hard to determine with some kind of quantitative measure. Variational autoencoders have a quantitative measure of its ability to cover the whole space of images in the distribution. And to me, that makes it, in that aspect, a much more compelling model. And in 2019, there was a development in variational autoencoders called the vector quantized variational autoencoders, and suddenly they became competitive with GANs in terms of image generation. So now you have a quantitative measure of whether you're covering the space, and you're able to generate very compelling images when you sample from the distribution. These are sampling from the distribution that has a quantitative measure of how much it's covering. And you can also do it, you can also do VAEs for Imagenet, class conditional. So this dog does not exist. This butterfly is still missing a head, I think. But anyway, it's a shocking development. So for me, I mean, we're going to do a lot of mathematics of deep learning. And we're going to do a lot of architecture of deep learning and go through, and if you take this class, you're going to be able to read the literature. You're going to understand all the terminology and the current state of the field. But in terms of this motivational unit, I want to leave you with the question of, will this Moore's law continue? And where are we going? And where will you, the students, take us? So thanks for listening.